Alright, so today we're going to take a look at Avogadro constant, mass, moles, molar mass and molecular mass, which is an absolute mouthful. The key point afterwards is to be able to convert between number of moles, number of particles and mass, which if you're taking chemistry you could probably already do, and to kind of prep ourselves and to get ourselves understanding what those terms actually are, we're going to calculate the molar mass and the molecular mass. Now if you're taking chemistry, it's entirely possible that you know how to do all of this already, in which case what I'd like you to do is make sure that you get the definition to Avogadro's number inside your notes. And then otherwise, if you're taking chemistry, this is fairly basic stuff. That being said, not everyone taking A Level physics also takes A Level chemistry, so we are going to take the time to go through this. If at any point when you're doing questions you think, yeah, I've got this is easy, then skip over the next set of questions. There's no point in doing, 5 to 10 questions in something that you think is trivial. So the first thing I want you to do is define Avogadro's number. Pause the video if you need some time to think about it. Did you say 6.02 times 10 to the 23 per moles? If you did, you would score 0 out of 1 for the definition. That is the value of Avogadro's number, but it's not a definition of Avogadro's number. And that value is actually given to you on your datasheet. It's called Avogadro's constant in physics, and it's given the symbol capital N with the subscript capital A. As far as the actual definition goes, there's two definitions for Avogadro's number. Either the number of atoms in 12 grams of carbon-12, or the number of particles, molecules, atoms in 1 mole of a substance. Particles is probably the better word to use there, seeing as molecules only fits if we have a bunch of molecules such as water or hydrogen gas, and then atoms only really fits if we have a bunch of atoms on their own, not bound into molecules, such as argon gas. Now, absolutely either of those definitions is fine, you just need to pick one and memorize it. But the second definition is more useful in a mathematical form. So from a physics perspective, the second definition helps us out because it's an equation that we need to remember. So while either of those definitions is fine for your examination, you probably, if you haven't memorized one for chemistry, you probably want to memorize the second one so that you can use it mathematically. So pause the video now to get one of these definitions into your book. So we're going to take a look at that second definition. Avogadro's number is the number of particles in 1 mole of a substance. And I want you to try to write that as an equation. So pause the video now so you've got a bit of time. So we should have Na equals capital N over lowercase n. Now that's a lot of n's. The capital N with subscript capital A is the Avogadro constant, which is on your datasheet, 6.02 times 10 to the 23 per mole. Capital N is the number of particles, and lowercase n is the number of moles. So that capital N and lowercase n match with what we use inside our ideal gas laws. Now, this relationship is something that you need to know, so I would highly recommend writing it down in your book. And this is just the mathematical way of expressing that second definition of Avogadro's number, which, again, if you don't need to remember a definition for chemistry, I'd recommend that you memorize this definition. Now, this definition of Avogadro's number links our two ideal gas law constants. And I'd like you to see if you could find the relationship between the molar gas constant R and the Boltzmann constant K. So those are the three equations, our two ideal gas laws, and the definition of Avogadro's number, the way that the two ends are related. So pause the video now and give that a try. So the first thing that we want to do is combine the two gas laws, and the left-hand side of both of those equations are the same, so we can set the right-hand side of those equations equal to each other, which gives us nRT is equal to nKT. Now there's a t on both sides, which we can cancel out. And then to match that with this up here, we want to get capital N over lowercase n so that we could substitute Avogadro's number in. So we need to rearrange this form for capital N over lowercase n. And then we could just substitute in Avogadro's number for the capital N over lowercase n. And then, for the fun of it, write it so that it doesn't have a denominator. So our three constants that we're using here are actually linked, which I think is quite interesting. Now note that this bit here is not a definition for Avogadro's number, even though this bit is a definition for Avogadro's number, so just don't get confused with that. And this is just an interesting tidbit, bit of extra information that I think is kind of cool. So remember that our ideal gas laws are empirical in nature. Now that means that the laws and constants were determined experimentally. What exactly would we need to measure in order to determine these experimentally? So if you want to give that a go without any hints, pause the video now. Otherwise, I'll give you a couple hints. So the first thing that you'll want to do is rearrange your ideal gas law for the constant, and then take a look at what measurements would need to be made in order to determine that constant from the equation that you have. And just to give you a hint, here are our two ideal gas laws. So we're trying to figure out what measurements we would need to make in order to determine R, and what measurements we would need to make in order to determine K. Pause the video now and give that a try. So hopefully with rearranging, we've got our constant equals PV over its appropriate N times T. So if we have a look at R, we can easily see we need to measure the pressure, the volume, the temperature, and the number of moles. How in the world are we going to measure the number of moles? And for K, again, we need the pressure, the volume, and the temperature, and the number of particles. I mean, we can't even see the particles, let alone count them. So how are we supposed to determine these? How are we supposed to determine the number of moles and the number of particles? That fourth measurement is mass. We can calculate the number of moles using this equation, which if you've taken chemistry, you've seen this before. And then using our previous definition of Avogadro's number, we can calculate the number of particles. So in this equation, we have a lowercase m for the mass of the sample in grams, an uppercase m for the molar mass of the substance in grams per mole, and a lowercase n for the number of moles. So this equation is one that you're expected to be able to use and know, but it is not given on your data sheet. So one that you definitely want inside your book, and one that you definitely want to memorize. Now how you memorize it is completely up to you, and we'll go through how I remember it in just a moment. There is a slight trick with this equation as well. The mass is measured in grams. Now the SI unit for mass is kilograms, but chemistry doesn't always use SI units. Chemistry sometimes uses CGS units, which stands for centimeter, gram, seconds. So there's still like factors of 10 from the SI units, which are meters, kilograms, and seconds, but they're not exactly the same, and we do need to be careful of that factor of 1,000 going from grams to kilograms and vice versa. So when you're using this equation, make sure that you're using grams. And then if you are going back to use an equation like mc delta theta or ml, this mass is in kilograms, just like all of the other physics stuff. So be careful with this one, and for the trouble that it causes, thank a chemist. Now this is an equation that you need to remember, and I used to always get it confused when I was in high school. So our teacher taught us mass is Mr. Mole, and the reason for that is it kind of tells us where things go. So mass, our lowercase m, is equal sign Mr. just being a capital M, right? Mr. capital M. Mole is the number of moles, n. So mass is Mr. Mole. So just to come back to our ideal gas law constants, for both of them we need to measure pressure, volume, and temperature. And then that fourth one for R is mass, where we can calculate the number of moles from mass equals Mr. Mole after we measure that mass. To determine K, we also want to measure the mass. And then from that, we can calculate the number of moles from mass is equal to Mr. Mole, and calculate the number of particles from the definition of Avogadro's number and our number of moles that we just calculated from our mass. So that capital M inside the equation is the molar mass, and that is the mass of 1 mole of a substance. Now, typically, you'll be given this inside the question. They could ask you to calculate it. I think it would be a bit silly of them to do, but they could ask you to calculate it. So we're just going to go through how to calculate the molar mass. And in order to calculate the molar mass, you need to know the molecular mass and how many molecules are in 1 mole. And the molecular mass of a molecule is the mass of a single molecule in atomic mass units. Now again, your exam might just give this to you in a question, or they might ask you to calculate it. It's highly unlikely that they'll ask you to calculate it, but it is entirely possible that they ask you to calculate it. And in order to calculate the molecular mass, you need to know the relative atomic mass of each element inside the molecule and how many of those atoms there are inside that molecule. Now for your physics paper, you are not given a periodic table. So your physics paper must supply you with all of that information, the relative atomic mass of each element that are in the molecule, how many of those atoms are in the molecule. So that's a lot of information that they'd have to give and a lot of work for something that is frankly more chemistry than physics, which is why it's a very unlikely question. That being said, it is a potential question. They could ask you for it. They do expect that you know it, but I haven't seen any questions where they've asked about it before. So you might already know how to do this. If you think you can, give this question a try, check your answer, and if you're comfortable with it, then skip ahead until you see the title molar mass. You will want a periodic table. Any periodic table will do that you get off the internet. So water is H2O. And that means water contains 2 hydrogen atoms, each with a relative atomic mass of 1 atomic mass unit, and water contains 1 oxygen atom with a relative atomic mass of 16 atomic mass units. So the total molecular mass of water is then 2 times the molecular mass of hydrogen and 1 times the molecular mass of oxygen, which gives us a total of 18 atomic mass units. Now, I find it's fairly easy to forget an atom or two when you're calculating a molecular mass. So I would recommend drawing a table with the headings elements, number of atoms, relative atomic mass, and total. So to give you an example, if they asked you to calculate the molecular mass of sodium chloride, you'd want to put sodium and chlorine as our elements. There is 1 sodium and 1 chlorine. And the relative atomic mass of sodium is 23.0. The relative atomic mass of chlorine is 35.5. So in order to calculate the total, we're going to go this number times that number goes in there. This number times that number goes in there. So we've got 1 times 23.0 gives us 23.0, and 1 times 35.5 gives us 35.5. And then we can add those up for the total of 58.5. So our molecular mass of sodium chloride is 58.5 atomic mass units. Now this one's a bit simple because there's only 1 sodium and 1 chlorine inside that molecule. So we're going to do another example with something that's a bit more complicated. So calculate the molecular mass of sulfuric acid. So we have got 2 hydrogens, we've got 1 sulfur, and we have got 4 oxygens. And then if we look on our periodic table, we can see the relative atomic mass of hydrogen is 1.0, relative atomic mass of sulfur is 32.1, and the relative atomic mass of oxygen is 16.0. So finding our totals, we've got 2 times 1 gives us 2, 1 times 32.1 gives us 32.1, and 4 times 16 gives us 64.0. Adding them all up gives us 98.1. So the molecular mass of sulfuric acid is 98.1 atomic mass units. And a third example that's a little bit more complicated, calculate the molecular mass of nickel acetate. So looking at this one, we've got 1 nickel. We have got, be careful with counting for the carbons because we've got 1 2 carbons inside this bracket, and we have 2 of those brackets. So we've got 1, 2 carbons times 2, we've got 4 carbons. We've got, again, careful with counting, 3 hydrogens, but then we've got 2 sets of those. So we have 3 times 2, 6 hydrogens. And with the oxygen, again, similar thing, be careful with counting, because we have 2 oxygens, but then we have 2 sets of what has 2 oxygens. So we have 2 times 2, or 4 oxygens. Now we look at our periodic table for the relative atomic masses, and nickel is 58.7, carbon is 12.0, hydrogen is 1.0, and oxygen is 16.0. Then finding the total for each element, 1 times 58.7 gives us 58.7, 4 times 12 gives us 48.0, 6 times 1 gives us 6.0, and 4 times 16 gives us 64.0. Adding those all up, we get 176.7. So our molecular mass of nickel acetate is 176.7 atomic mass units. Now, if you're feeling pretty good with those, that's absolutely fantastic. Skip ahead to the molar mass section. If you're not feeling very good with them, then give these ones a try and do them one at a time, and then play through the video sort of one at a time. So I'll show you the answers one at a time. So you can try a question, get the answer, try a question, get the answer. So you could try and check. Once you're starting to feel comfortable with them, again, move on to the molar mass, because while this helps our understanding in physics, I highly doubt your exam will ask this of you. So pause the video now if you want to give these a try, because I'm going to start showing the answers. Question 1 should be 102.9 atomic mass units. Question 2, 126.9 atomic mass units. Question 3, 303.3 atomic mass units. Question 4, 74.1 atomic mass units. Question 5, 164.0 atomic mass units. That 0.0 should be there for significant figure reasons. Question 6, 96.0 atomic mass units. Again, that 0.0 should be there for significant figure reasons. Question 7, 180.0 atomic mass units. Again, we should have that 0.0 for significant figure reasons. Question 8, 357.4 atomic mass units. Question 9, 68.1 atomic mass units. And question 10, 183.4 atomic mass units. So molar mass is the mass of 1 mole of a substance. In order to calculate the molar mass, you need to know the molecular mass and how many molecules are in 1 mole. So we're going to start with our previous example of sodium chloride, which we found its molecular mass to be 58.5 atomic mass units. So our molecular mass of sodium chloride is 58.5 atomic mass units, and we need to get that into a proper mass unit of grams. So 1 atomic mass unit is 1.66 times 10 to the minus 24 grams. Doing that conversion gives us a molecular mass of 9.711 times 10 to the minus 23 grams. In order to calculate the molar mass, we have the molecular mass, or mass per molecule, times the number of molecules per mole. Now, how many molecules are in 1 mole? That is Avogadro's number, 6.022 times 10 to the 23. Asking how many molecules are in 1 mole is similar to asking how many eggs are there in a dozen, or how many years are there in a score. A dozen, a score, Avogadro's number are all set numbers. So our molar mass equals mass per molecule times number of molecules per mole is simply just our molar mass, capital N, times our molecular mass, which is our mass per molecule, times Avogadro's number, which is the number of molecules per mole. So going back to our example of sodium chloride, we had a molecular mass of 9.711 times 10 to the minus 23 grams, which is per molecule. And we know that Avogadro's number is the number of molecules per mole, which is 6.022 times 10 to the 23. Plugging that into our equation gives us an answer of 58.5 grams per mole. Now, notice that this is exactly the same as our molecular mass, except it has a different unit. our molecular mass was 58.5 atomic mass units, and our molar mass is 58.5 grams per mole. And this works, and it works every single time because of the definition of the atomic mass unit. So you can calculate the molar mass the same way as the molecular mass, but make sure you use the different units. Or, if a question gives you molecular mass, you can just change the units on it and treat it like the molar mass and use it for whatever you need. Whether you need it in the form of molecular mass or molar mass is absolutely fine. Just be careful with the units. In terms of your notes, I would probably get something to this effect down into your notes so that you know when you're reading back that you can use that. And make sure that you have the units with it as well, that molar mass would be in grams per mole and molecular mass would be in atomic mass units for those two values to be the same. And again, if you'd like some more practice with it, feel free to go through these questions. Otherwise, skip ahead to the next slide, which is likely examination questions. So if you want to have a go at these questions, pause the video now, try question 1, and then play it so that you can see the answer to question 1. Pause, play, pause, play. So question 1 should be 71.0 grams per mole. That 0.0 should be there from significant figure purposes, and make sure that you've got correct units of grams per mole because this is molar mass and not molecular mass, which is measured in atomic mass units. Question 2, we should have 56.1 grams per mole. Question 3, we should have 80.0 grams per mole. Question 4, we should have 98.0 grams per mole. Question 5, we should have 121.0 grams per mole. Question 6, we should have 58.3 grams per mole. Question 7, we should have 132.1 grams per mole. Question 8, we should have 60 grams per mole. Question 9, we should have 331.2 grams per mole. And question 10, we should have 379.7 grams per mole. Now your exam is really likely to give you the molecular mass or the molar mass of the substance in question. It's highly unlikely, but probable, which is why we did it, that they ask you to calculate the molecular mass or the molar mass. And if they do ask you to calculate it, it's probably going to be for a fairly simple molecule, such as nitrogen gas or oxygen gas, which is just, 2 nitrogens or 2 oxygens respectively. Now your exam is quite likely to ask you for an ideal gas law quantity, such as the number of particles or the number of moles from the mass or vice versa. And the idea behind this is that you're taking the physical quantities that you're measuring, the temperature, pressure, volume, and mass, and then being able to convert into things that you can use the ideal gas law equations for, so converting that mass into one of the ends, or the other way. They've given you the ideal gas law quantities such as the pressure, the volume, the temperature. Maybe you've had to read these off a graph, and then they've asked you to calculate the mass of that sample that there is. So that would require us to use one of our ideal gas laws to calculate either the number of particles or the number of moles, and then from there calculating the mass. So when we do that, these two equations are key, the definition of Avogadro's number and mass is equal to Mr. Mole, but neither of these are given on your exam, so you need to make sure you know these. And just to recap for these equations, our uppercase N with the subscript capital A is the Avogadro constant, or 6.02 times 10 to the 23 per mole, which is given on your data sheet under the constant section. The capital N is the number of particles, lowercase n is the number of moles, little m is the mass of the sample in grams, be careful, not kilograms, in grams, and capital M is the molar mass of the substance in grams per mole. Remember that the molar mass is the same as the molecular mass as long as you're using the molar mass in grams per mole and the molecular mass as atomic mass units. So these questions here probably closer resemble what you could expect from your exam. Calculate the mass of each of the following, and each of them gives you either the molar mass or the molecular mass. So have a go at these. Maybe try, if you're feeling very confident with it, try number 1 and then try number 4 so that you're using one with the molar mass and one with the molecular mass. But if you're feeling really confident with these, again, feel free to skip ahead to the next section, which is calculating the number of moles from the mass. Just like the other questions, I'll show the answers one at a time, so you can pause the video, try question 1, and then I'll display question 1, and then you can pause the video again, and then it'll display the answer to question 2 after that. So pause the video now. So question number 1, we should have 35.5 grams, remembering that it is grams and not kilograms. Question number 2, we should have 230 grams. Question number 3, 1.92 grams. Question number 4, 61.4 grams. And question number 5, 630 grams. This set of questions is exactly opposite of our last set, so it's calculating the number of moles from the mass given, and notice that the molar mass or the molecular mass is given. So again, pause the video, give the first question a try, display the first answer, then pause the video, give the second question a try, until you feel comfortable with these. Once you feel comfortable with these, move on to the next set of 5 questions. Pause the video now. So question 1, we should have 0.0990 moles. Now, realistically speaking, it should just be to 2 significant figures because that 9.7 grams. That being said, this is likely to be a number that we use in a subsequent calculation, so we should be giving an extra significant figure just so that when we use it in our subsequent calculation, we aren't getting any rounding errors. Question 2 should be 2.83 moles. Question 3 should be 3.36 moles. Question 4 should be 0.364 moles. And question 5 should be 0.457 moles. For this set of questions, calculate the mass from the number of particles given. So this will require the use of both of those equations, the definition of Avogadro's number and then our mass equals Mr. Mole. Just like all the other ones, pause the video, give it a try, play it to see the answer, pause the video, give it a try, and so on and so forth. When you're feeling quite comfortable with these ones, go on to the next set of questions, which is calculate the number of particles from the mass. For question 1, we should have 353 grams, again being careful that it's grams and not kilograms. For question 2, 31.8 grams. For question 3, 18.2 grams. For question 4, 7.44 kilograms. So if you have that in grams, it should be 7,440 grams. And question 5, 62.4 grams. For these sets of questions, you're calculating the number of particles from mass. So you'll need to use mass as Mr. Mole to get your number of moles, and then you'll need to use the definition of Avogadro's number in order to get the number of particles. Just like the other ones, pause the video, play it for the answer, pause the video, play it for the answer, so on and so forth. If you're feeling quite confident and quite comfortable with these, you do not have to do all 5 and you can skip ahead to the key points. So if you can give question number 1 a try, pause the video now. Question 1 is 5.37 times 10 to the power 22. Notice that when we're dealing with number of particles, it's always going to be a rather large number, and they'll probably be times 10 to the 22 to times 10 to the 25, maybe as low as times 10 to the 20, but it's always going to be times 10 to the, and then a number in its low 20s. If you've got a number that's considerably out from there, you want to double check your work. Question number 2, we should have an answer of 1.09 times 10 to the 25. Notice that this is a rather large power, but that being said, we've got 2.4 kilograms. So, the large power is due to the fact that we've got kilograms as opposed to just factors of grams, which gives us times 10 to the 22-ish. So kilograms gives us an extra 1,000, which would make sense. We've got an extra 1,000 there. Question 3, we should have 7.12 times 10 to the 22. Question 4, we should have 5.31 times 10 to the 23. And question 5, 3.57 times 10 to the 23. So the key concepts from this lesson. So the first thing is definition of Avogadro's number. Either of these definitions are fine, pick one and memorize it. Either the number of atoms in 12 grams of carbon-12 or the number of particles in 1 mole of a substance. That second definition of Avogadro's number gives us the equation Avogadro's number is equal to the number of particles divided by the number of moles. That is an equation that you need to memorise. If you're not doing chemistry, I'd recommend that you just memorise the second definition of Avogadro's number, since you need that equation and they link together. The constant and the ideal gas laws are determined experimentally. And then we use the rearrangement of our ideal gas laws to determine R and K. So in order to determine our molar gas constant R and our Boltzmann constant K, we need to measure the pressure, the volume, the temperature, and the mass, although the mass isn't used in these equations directly. Then we can use our equation mass is Mr. Mole in order to calculate the number of moles from our measured mass. And if we're trying to find K, we can then use the definition of Avogadro's number to convert from the number of moles into the number of particles. And for this equation, M is the mass in grams. We need to be careful that it's not our SI units of kilograms. Capital M is the molar mass in grams per mole, and this value is equal to the molecular mass in atomic mass units. And N is the number of moles. And that's everything that you need to know about Avogadro's constant, mass, moles, molar mass, and molecular mass inside the thermal topic for your exam. Have a fantastic day.